All right, number 11 of the practice exam for a practice final for Calculus 3 tells us or asks us to set up an integral in spherical coordinates representing the volume of the upper hemisphere of radius 3. And so the upper hemisphere of radius 3 looks like this. It's 1/2 or the top half of the sphere. You, of course, know the answer to this question. I mean, the volume of the question, but the volume of this hemisphere is 1/2 of what? 4/3 times pi times 3 cubed. You can easily obtain that. But the point is, for you to show or demonstrate your understanding of the spherical coordinates and triple integral by writing the triple integral that represents that volume correctly. All right. So what do you have? Well, okay, so you have to have, so dv in spherical coordinates is, remember, rho square sine phi d rho d phi d theta. All Greek to me, right? Yeah, rho, phi, and theta are all Greek letters. So theta goes from what to what? Well, that's easy because it goes through the entire circle, 0 to 2 pi. Phi goes from what to what? Maybe this is the trickiest part. Phi goes from 0, which is here, all the way to where you hit the xy plane. And that's pi over 2, 90 degrees, right? From here, you go 90 degrees in all directions to get to the equator of the sphere, which is, the boundary of this hemisphere. And so 0 to pi over 2, those are the bounds for phi. And then rho, of course, is going from 0 to 3, so you can find the solid without any holes inside. And so that's pretty much it. The volume is going to be the triple integral from 0 to 2 pi, another integral from 0 to pi over 2, another integral sine 0 to 3, and then rho square sine phi d rho d phi d theta. And if you are to work this out, of course, the first one will always be, 1/3 rho cubed sine phi, and then you go from 0 to 3 and so on. And if you actually work this out, you will get the correct answer. By the way, what is the correct answer? You don't have to do this part. You are not asked to do this, but if you are to find this, it's 1/2, since it's a hemisphere, of 4/3 pi, and then r cubed, 3 cubed, right? So that's going to be 3 squared. And this is going to be 2. It looks like it's 2 pi times 9. That should be 18 pi is what you should get. But you can check that to make sure that this is correct. All right. Number 12 has to do with the line integral. Okay, so now we're going into chapter 6. The line integral, to find x plus y, and you have to find this very simple looking object, right? So what is that? Well, this, in order to calculate this, you actually have to parameterize this c. That's not hard. Okay, so this is 6 cosine t, 6 sine t, as t goes from 0 to not 2 pi. You only go a quarter of a circle, so that's pi over 2, right? And so you will do that, but you have to express f in terms of t, and then you have this annoying term you have to add, which is the speed, and then you have to do this dt. So by the way, just writing this down at the beginning may help you remember the procedures or the process you have to take in order to get to the answer, okay? Because you know that everything has to be in terms of t, right? T goes from 0 to pi over 2. All right, so I do need the derivative. Oh, yeah, so here I start with this, right? And I do need the derivative, which is -6 sine t, 6 cosine t. And I have to find the norm of the derivative. In this case, it's pretty simple. I think you can see it's square root of 36 times what becomes 1. So that's just 6, right? And so that will be right here. And f of xy is x plus y, but that's just 6 cosine t, that's x, plus 6 sine of t, right? So the answer to this question is, let's go ahead and start a new line here. this will be the integral from 0 to pi over 2 of 6 cosine t plus 6 sine t dt. But before dt, I have something else, right? You have to have 6 and then dt. Okay, I have 6 here and 6 here. Let's just take this out. That's 36 cosine t plus sine t dt. All right, so I factored out these two sixes. They come out as a 6. And then you have this 6. So 6 times 6 is 36. I took it outside of the integral sign, and this is what you get. All right, so that's what's the antiderivative of cosine. That's sine. And antiderivative of sine is cosine, right? Whoops, that's not it. That's negative cosine. All right, so then you go from 0 to pi over 2, 36. All right, so what's the sine of pi over 2? 1. Cosine of pi over 2 is 0. And then sine of 0 is 0. Cosine of 0 is 1. So you have to be very careful with negative signs. Extremely careful about negative signs because they can throw you off, giving you wrong answers every other day or so. All right, so it's 36, and then it's 1, minus 0, plus 1, right? So the answer is 72, and that is the value of the line integral in question. All right, let's go to number 33. I am going to write down the problem first. Okay, number 13 gives us a vector field, capital F, and C, the curve is the straight line segment from 0, 0, 0 to 2, 2, 2. And we are to find the work done by F along C. Okay, so what's work? How do you find work? Not like finding a job, right? Finding the work. Well, the work is, if you remember, it's work along a curve is F dot, well, the definition is T ds, right? Because this dot product gives you the force in the direction of the motion. But more practical way to remember this is to write F dot dr. Or for our purposes, it's really dot r prime dt, right? And so you have to know this much before you actually do the problem, right? So that means you have to have parametrization of C. This is a straight line segment, so you can do TTT if you, or you can do 2T, 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 and let T go from 0 to 1. It's up to you, but I think TTT may be easy. You let T go from 0 to 2, right? So you can go from 0, 0, 0 to 2, 2, 2. You also have to have the derivative of this. That's not too bad. That's going to be 1, 1, 1. So simple. And then you also have to have F written in terms of T. Now, in this parameterization, X, Y, and Z are all T. See that? So this will just become negative. This will just become negative 3T, 6T, 6T. All right, you have to have the dot product. So let's just go ahead and find the dot product. All right, so that's going to be negative 3T plus 1 times 6T plus 1 times 6T. That's 9T, right? And so that's simple, right? So the work is the integral from 0 to 2 of the dot product 9T dt. It seems so simple, right? But that's really what's required here. And then integrating, you get 9 over 2, and then 4 minus 0, that's 9 times 2. The answer is 18, and that's fine. Now, if you happen to choose the other obvious parameterization, which is 2T, 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 T goes from 0 to 1, these will become all 2s, right? 2, 2, 2. And then these will change. But when you take the dot product and integrate it from 0 to 1, you will get 18. You may want to try that just to verify it, but you will get the same answer because the work done by F does not depend on your parameterization or anybody else's parameterization as long as it's correct. Okay, so that's number 13. Moving on to number 14, we read, suppose C is any curve from 100 to 420. Notice here, they did not specify which curve it is, right? That tells you what kind of question it is, by the way, right? F is given as a vector field along C, but C is any curve from this point, initial point, to this terminal point. And so that implies that the answer does not depend on the path from this initial point to the terminal point. That means it must be involving the fundamental theorem of line integrals, right? Because it's path independent, which means that this must be what? A conservative vector field, meaning that it must have a potential function, right? So the whole idea is to find f such that the gradient of f is capital F. Right, so how do you find a potential function? Oh, by the way, if you are still curious about, whether this is a conservative vector field or not, you can do that test, PQR. You have to show that, PX is equal to QI and so on. But you don't have to do that because if you can, first of all, because the question reads like you have to use the fundamental theorem of line integrals, right? If this were not conservative, the problem wouldn't make sense because it says any curve from this point to that point. And the answer will say, well, no, it varies. It depends on the path you take from this point to that point. The fact that the question is asking you to find the work only based on this tells you that it must be a conservative vector field. Now, a lot of people have asked me over the last many years, how do you so quickly find a potential function? There's really no magic there, right? Once you guess or determine that this is a vector, this vector field is conservative, try to find f, which is a function of x, y, z, so that when you take the partial of f with respect to x, you get negative 5y. So that means you have to have negative 5xy as a term, okay? And if you differentiate y, f with respect to y, you get this. So that means you have to have negative 5xy as before. You also have to have 3y e to the zth power in order for you to get this term in fy, right? So take a look. At this point, you have this. Or at this moment, we have this. The partial of this with respect to x is negative 5y. With respect to y is negative 5x plus 3 e to the z. So that's that. But if you take the derivative of this with respect to z, you should get this. Now, from this part here, if you differentiate this second part, section or term with respect to z, you do get 3y e to the z. So that part is okay. But you also have 5. How did that happen? Well, you must have a positive 5z here in order for this 5 to appear here as a part of fz, right? So that's how you find your potential function. Now you can, plus c here. You don't have to because you're looking for just one potential function. So there it is, okay? So now all you have to do is to plug in this potential function, well, into this potential function. Let me go ahead and write this. Evaluate this at the initial point, terminal point, and find the difference. Okay, so let's go ahead and put the terminal points here. Negative 5 times xy, that's 4 times 2, plus 3y e to the 0. E to the 0 is not 0, right? Be careful here, it's 1. And then 5 times 0, that's 0. So that's the first part. Now, if x and y are both 0, you get, well, if y is equal to 0, this part is 0. If y is 0, then the second part is 0. If z is 0, this third term is also 0. So there is nothing to worry about for the when you enter 1, 0, 0. Okay, so now let's go ahead and find this. That's negative 40 plus 6 plus 0. And that turns out to be negative 34 if I did my arithmetic right. And that is the answer to that question. All right, let's go to number 15. The question about Green's theorem. Let me go ahead and write that question. All right, number 15 is a question on Green's theorem. You're given the vector field, two-dimensional, because it involves Green's theorem, and the domain D, whose boundary is the curve C, and that goes from 0, 0 to 2, 0 to 2, 4 to 0, 4, and back to the origin, right? It has to be enclosing a region, the domain D, which in this case is a rectangular region. The vector field is given, and you have to find the work done by F along C. And what Green's theorem says is that this is equal to the double integral of Qx minus Py. These are the partials of these, right? This is P and this is Q. And you are to integrate it inside D. Okay, not, I mean, see, the thing is, this is a line integral. This only has to do with the boundary. And this has to do with a double integral. That is the inside that you're integrating over the domain D, the two-dimensional domain D. So that's what Green's theorem says. Okay, so what is Qx minus Py? That really is the crux of this question here. Qx is simple, 1. Py, if you take the derivative of this with respect to y, you get minus 2, well, 2y. And of course, the sign between them is negative. So you do that. That's an easy question then, right? Because the work done by F along the boundary turns out to be the double integral from 0 to 2, 0, 4, and 1 minus 2y dy dx. Rectangular region, you want to use the rectangular coordinate system. All right, that's really the hard part. The rest is easy. You integrate this with respect to y, you get this y minus y squared, whose derivative is that. And so let's calculate that. That's 4 minus 16 minus 0. So that's negative 12. And then you just have the integral from 0 to 2 of dx. That's negative 24. And that happens to be the work done by F as you go around the region or the boundary C. You can also directly calculate this by parameterizing each of these sides. You have to have 4 parameterizations because the C consists of 4 components or 4 different parts. And then you can try to find the line integrals of all 4, and then you can add them together. You can verify that the answer is negative 24. All right, we'll take another break, and then we will do 16, 17, 18, and 19 in our last segment.